Hello friend, welcome. If this is your first visit, this channel is a quiet corner where big ideas in science are told softly, so you can drift off while learning something beautiful. Tonight we're taking a slow walk to the far edges of time, asking how the universe might end and what that means for us without formulas, hype, or hurry. Let's begin. Chapter 1. The Cosmic Question. Does the universe have an end? To ask whether the universe has an end is to press physics on what it can and cannot say about time, change, and the large-scale behavior of nature. The word end hides several possibilities. It might mean a finite moment in the future at which the known laws reach a boundary. It might mean a slow exhaustion of free energy in which nothing new can occur because every gradient that drives structure and life has flattened. Or it might mean an end to what we can observe, even if the universe beyond our reach continues. In cosmology, these notions must be expressed in precise terms about space-time geometry, energy content, and the statistical behavior of matter and radiation. The scientific version of the question is not, will everything stop? But, given the laws of physics as we understand them, and the measurements we have made, what are the allowed long-term behaviors of the cosmos? Modern answers start from two pillars. The first is general relativity, which links space-time curvature to the energy and momentum of whatever it contains. Assuming that on very large scales, the universe is homogeneous and isotropic, Einstein's equations simplify to describe how the scale factor, the measure of cosmic distances, changes with time. The second pillar is observation. Galaxies are redshifted in proportion to distance. The cosmic microwave background reveals the geometry of space, and the distribution of galaxies shows how structure grew. Together, theory and observation define a working model in which space is nearly flat, matter is mostly dark, and the expansion has been accelerating for the last 5 billion years. The fate of the universe depends on how each component of its energy budget evolves. Matter dilutes as space expands. Radiation dilutes and also loses energy as its wavelength stretches. Vacuum energy associated with a cosmological constant does not dilute at all. Its density remains constant as new space is created. Because these components scale differently, their relative importance changes with time. Radiation once dominated, then matter, and if vacuum energy is constant, vacuum domination is permanent. That late-time vacuum domination drives the universe toward an exponentially expanding state that resembles de Sitter space, in which observers are surrounded by an event horizon and can access only a finite region. This already introduces one sense of an end. Even if physics continues forever, there can be an end to cosmic connectedness. Our local group of galaxies is gravitationally bound and will merge into a massive remnant, but more distant clusters will eventually recede beyond an event horizon defined by accelerating expansion. Their light will be redshifted into wavelengths so long that no detector could ever see it, and then beyond contact altogether. From the vantage of future observers, the night sky will slowly empty. They will live in a universe that appears isolated and static, even though on larger scales it continues to expand. Thermodynamics provides a second lens. The second law states that the total entropy of an isolated system does not decrease. If the cosmos expands and cools without bound, then energy gradients that now power stars, planets, and life will diminish. Gas in galaxies is consumed, heated, or locked into remnants. Stellar populations age. Radiation shifts to longer wavelengths and lower temperatures. In this picture, often called heat death, the universe approaches a state of maximum entropy in which no macroscopic free energy remains to do work. This is not an end at a moment, it is an end of possibilities. Astrophysics lets us put timescales on that narrative. Star formation cannot continue indefinitely because galaxies hold finite gas and because inflow from the intergalactic medium weakens as expansion accelerates. The massive, short-lived stars vanish first. Sun-like stars last billions of years. Low-mass red dwarfs can burn hydrogen for trillions of years, so the era of starlight extends far beyond the present, but it is not infinite. After the last stars fade, what remains are stellar remnants, white dwarfs, neutron stars, and black holes, orbiting within merged galaxies. Black holes dominate the entropy budget of the universe and are central to its long-term thermodynamics. In semi-classical gravity, they are not truly black. Quantum effects make them radiate at a temperature inversely proportional to their mass. For stellar and supermassive black holes, this temperature is far below the cosmic microwave background today, so they absorb more than they emit. But in a distant future, when the background has cooled, they begin to evaporate. The timescales are immense. A black hole with the mass of the Sun takes on the order of 10 to the power of 67 years to radiate away. Supermassive black holes take far longer. When they finally go, they end in a burst of high-energy radiation, returning their mass to the dilute bath of particles that fills space. All of this assumes dark energy behaves exactly like a cosmological constant. That is a simple and successful hypothesis, but it is not yet derived from deeper theory. A more general framework characterizes dark energy by its equation of state parameter W, the ratio of pressure to energy density. A cosmological constant corresponds to W equals -1. If W is slightly above -1 and constant, the expansion still accelerates but more slowly. If W is below -1, called phantom behavior, the effective energy density increases as the universe expands. In such a case, the scale factor can diverge in finite cosmic time, producing a future singularity called the Big Rip. Bound systems are torn apart as tidal forces overwhelm every binding force. Observations today constrain W to be very close to -1, but modest deviations are not ruled out. If the universe exhibits phantom behavior, the end is not a slow equilibrium, but a finite time catastrophe. There is a mirror alternative. Perhaps the current acceleration is transient. Before the discovery of acceleration, many cosmologists expected a matter-dominated universe dense enough to recollapse in a big crunch. In the simplest models that match present observations, that outcome is disfavored. Yet if dark energy is dynamical and can change sign or decay, the late-time behavior could shift. Some proposals, often grouped under cyclic cosmologies, envisage repeated phases of expansion and contraction. Whether such ideas can be reconciled with precision data and quantum gravity is uncertain, but they remind us that a recollapsing end is not impossible in principle. Quantum field theory introduces a different kind of ending that is abrupt rather than gradual. The vacuum we inhabit could be metastable, a false vacuum, rather than the absolute lowest energy state of the fields. If so, quantum tunneling could nucleate a bubble of a lower energy vacuum. The bubble wall would expand at nearly the speed of light, and the interior would have different physical parameters. Within that bubble, the structures that existed before could not survive. Calculations suggest our vacuum is either stable or metastable, with a lifetime vastly longer than the current age of the universe. But physics beyond the standard model could alter that. Vacuum decay would not announce itself in advance. It would simply occur somewhere and expand outward. That makes it a genuine end in the strongest sense for any observers in its path, even though from a global perspective, time still evolves. All of these possibilities are constrained by data. The acceleration of the universe is inferred from supernovae, the pattern of acoustic peaks in the microwave background, the scale of baryon acoustic oscillations in galaxy surveys, and gravitational lensing that maps the growth of structure. Together, these measurements support a spatially flat universe with a dark energy component whose effective W is close to -1. They leave room for evolution and dynamics, but not much. They also indicate that the age of the universe is finite in the past and that the hot Big Bang describes a real thermal history. None of these measurements can yet tell us whether protons decay or whether the vacuum is absolutely stable, and none excludes small deviations in dark energy behavior that would matter over trillions of years. There are nearer ends distributed across smaller scales. Long before the last red dwarf fades, galaxies will have transformed most of their gas into stars or heated it beyond recovery. The Milky Way and Andromeda are on a collision course and will merge in a few billion years, feeding their central black holes with a final burst of activity. Planetary systems evolve. Stars like the Sun end as white dwarfs with faint debris disks. For biospheres and civilizations, these milestones are the relevant ends. Cosmology provides the boundaries, but local astrophysics writes the chapters that matter for life. Given this landscape, the most careful answer to the question, does the universe have an end, is conditional. If dark energy is a true cosmological constant, and the vacuum is stable, then the universe does not end at a moment. It expands forever, while the range of phenomena steadily diminishes. If dark energy is phantom-like, the universe could have a finite lifetime ending in a big rip. If acceleration someday reverses, the universe could recontract in a big crunch. If the vacuum is metastable, a decay event would end the observable universe for any observers within the expanding bubble. Current observations favor the first option, but they do not logically exclude the others. Physics treats this question operationally. We translate end into measurable parameters, the equation of state of dark energy, the stability of the vacuum, the possibility of proton decay, the validity of black hole evaporation, the geometry of space, and the long-term star formation rate. We design observations and experiments to constrain those parameters. In doing so, we shift the conversation from myth and metaphor to models and evidence, without losing the grandeur of what is at stake. On human timescales, the universe has no end at all. The intervals between these milestones dwarf any history we can imagine. Yet there is meaning in situating ourselves within that immensity. Knowing that the cosmos admits intelligible futures, even if they are cold or strange, makes our moment feel like a sentence in a very long story. The stars will not last, but for now curiosity still burns brightly. Chapter 2. The Expanding Universe, From the Big Bang to Now. The story of cosmic expansion is central to astrophysics, not only because it defines how the universe has evolved, but also because it frames every question we ask about its future. When we say the universe is expanding, we are not describing galaxies moving through static space in the way ships cross an ocean. We are describing the stretching of space itself, the change in the metric that measures distances between objects not bound together by gravity. This idea is so counterintuitive that it took decades to gain acceptance, but today it is one of the most secure foundations of cosmology. The modern picture begins with Einstein's general theory of relativity. When Einstein wrote his field equations in the year 1915, he had no intention of describing a dynamic universe. He believed, as did most scientists of his time, that the cosmos was static and eternal. His equations, however, suggested otherwise. Solutions found independently by Alexander Friedmann in Russia and Georges Lemaitre in Belgium showed that a homogeneous, isotropic universe would either expand or contract. These solutions implied that the cosmos had a history, that it might have begun in a dense, hot state and could evolve into something very different. Einstein initially resisted this conclusion, adding what he called the cosmological constant to counteract gravitational attraction and preserve a static universe. It was a temporary move. Observations soon revealed that galaxies were not at rest, but receding from one another in a systematic way. In the 1920s, Edwin Hubble and his collaborator Milton Humason measured the redshifts of galaxies and established that the more distant they were, the faster they receded. This was not motion through space, but evidence that the very fabric of space was stretching. Suddenly, the theoretical solutions of Friedmann and Lemaitre matched the data, and the expanding universe became unavoidable. From that moment, the cosmic narrative shifted. If the universe is expanding today, it must have been smaller in the past. Extrapolated backward, this reasoning suggested a beginning in an extremely dense state. Lemaitre called it the primeval atom, a poetic description of a universe born from a single point-like state of extraordinary density. By the 1940s and 50s, theorists began to connect this idea with observable consequences. A hot early universe would have produced nuclear reactions, forging light elements such as helium and deuterium. It would have left behind a bath of thermal radiation, cooled and stretched by expansion but still detectable. These predictions set the stage for observational tests. The decisive evidence came in the 1960s when Arno Penzias and Robert Wilson detected the faint glow of microwave radiation coming from all directions. This cosmic microwave background was quickly interpreted as the cooled remnant of the hot early universe, with a spectrum nearly identical to that of a perfect blackbody. Its discovery cemented the Big Bang model, not as a speculative idea, but as a framework solidly tied to data. In the decades since, satellites such as COBE, WMAP, and Planck have mapped the microwave background with increasing precision, showing temperature variations on the order of 1 part in 100,000. These fluctuations are the seeds from which galaxies and clusters later grew. The expansion of the universe is not uniform over time. Different forms of energy density dilute differently as the scale factor grows. In the earliest fractions of a second, radiation dominated, and the universe was opaque, a dense plasma of particles and photons coupled tightly together. As expansion continued, matter became more important, allowing atoms to form in the process called recombination. Light could then travel freely, producing the microwave background we observe today. In this matter-dominated era, gravity slowed the expansion and allowed structures to form. Galaxies coalesced, stars ignited, and cosmic history as we know it unfolded. For much of the 20th century, cosmologists debated whether this expansion would continue forever, slow to a halt, or reverse in a collapse. The answer hinged on the universe's density. If the density were above a certain critical value, gravity would eventually overcome expansion, leading to recollapse. If it were below that value, expansion would go on indefinitely. For a time, the universe appeared to sit near this critical point, and large surveys of galaxies sought to measure the balance more precisely. Then, in the late 1990s, a profound discovery changed the picture. Two independent teams studying distant supernovae found that the expansion of the universe was not slowing, but accelerating. This was completely unexpected. The data implied that some form of energy, later called dark energy, was driving the expansion faster over time. The simplest explanation was a cosmological constant, a fixed energy density of empty space. But whether it is truly constant or something more dynamic remains an open question. Today, the concordance cosmological model, sometimes called lambda cold dark matter, with lambda representing the cosmological constant, describes an expanding universe made mostly of dark components. About 70% of the energy density is dark energy, roughly 25% is dark matter, and less than 5% is ordinary matter. Radiation is negligible at present, though it dominated in the first 100,000 years. This balance explains not only the observed acceleration, but also the large-scale structure of galaxies and the details of the microwave background. The expansion has left imprints on every scale. On the largest scales, galaxy surveys reveal the cosmic web, filaments, clusters, and vast voids shaped by the tug-of-war between gravity and expansion. On smaller scales, expansion determines the ultimate fate of galactic neighborhoods. Bound systems, such as our local group, resist expansion through gravity, but unbound galaxies drift ever farther apart. As time progresses, expansion will render distant galaxies invisible, their light stretched to wavelengths too long to detect. The pace of expansion is measured by the Hubble constant, named after Edwin Hubble. Determining its precise value has proven surprisingly difficult. Different methods, measuring supernova distances, observing the microwave background, or analyzing gravitational lensing, have yielded slightly different answers. This Hubble tension remains one of the most discussed puzzles in cosmology. Its resolution could point to subtle physics beyond the current model, perhaps involving the nature of dark energy or the behavior of neutrinos. The concept of expansion also reshapes our understanding of horizons. Because light travels at a finite speed, we can only see a finite volume of the universe, the observable universe. Beyond that lies a vast region permanently beyond our reach. Expansion means that galaxies now visible may one day recede faster than light relative to us, not by breaking relativity, but because space itself stretches. This creates an event horizon, a boundary beyond which signals can never reach us. In this way, expansion defines not just the universe's history, but the limits of what can ever be known. One of the most intriguing episodes in expansion theory is inflation. Proposed in the 1980s, inflation posits that in the earliest fraction of a second, the universe underwent an extremely rapid expansion, increasing its size by many orders of magnitude. This process explains why the universe appears so uniform on large scales and why its geometry is nearly flat. Quantum fluctuations during inflation would have been stretched to cosmic scales, providing the seeds for galaxies and clusters. Observations of the microwave background support this picture, though the exact mechanism remains uncertain. If inflation is correct, expansion is not only a feature of the universe's later history, but the key to its very structure. The physics of expansion has practical consequences for astrophysics. The age of the universe, currently estimated at about 13.8 billion years, is inferred from models that incorporate expansion. The size of the observable universe, about 93 billion light-years in diameter, reflects not just the distance light has traveled, but the fact that space itself has expanded while that light was en route. Even the chemical composition of the universe, with about a quarter helium by mass is a relic of nuclear reactions in the hot early stages of expansion. Looking forward, expansion will continue to shape cosmic destiny. If dark energy remains constant, galaxies beyond the local group will drift irreversibly away. Over tens of billions of years, only our gravitationally bound neighborhood will remain visible. The universe as experienced by far future observers will be vastly more empty and silent than it is today. Expansion does not merely describe the past, it writes the script for the future. The expanding universe is thus more than a physical fact, it is a framework. It tells us that we inhabit a cosmos with a history, that the structures we see today grew from tiny fluctuations in an earlier, hotter state, and that the universe is not static but dynamic, governed by laws that can be tested and refined. Expansion transforms space from a passive stage into an active participant, shaping everything from the behavior of galaxies to the possibility of cosmic horizons. On human scales, expansion is imperceptible. Atoms, planets, and even galaxies are held together by forces far stronger than the gentle stretching of space. Yet across the unimaginable reaches of billions of light years, expansion is the dominant fact of existence. To live in such a universe is to accept that nothing remains fixed on the grandest scales, that time and space themselves are evolving, and perhaps there is something existential in that realization. The cosmos is not a static backdrop, but a process, a story unfolding across eras far longer than human imagination can fully grasp. We are brief participants in the story, but through science we glimpse its structure, and in that glimpse find a measure of belonging to a universe that is still, even now, expanding. Chapter 3: Dark Energy and the Mysterious Cosmic Push. When the discovery of the accelerating universe was announced in the late 1990s, it marked one of the most unexpected turns in modern science. For decades, cosmologists had debated whether the expansion of the universe would continue forever or eventually slow and reverse. Few imagined a third option, that expansion might not only persist but speed up over time. Yet this is what the data revealed, and the force behind this phenomenon has come to be known as dark energy. The phrase dark energy is intentionally broad. It does not identify a substance in the ordinary sense, nor a field we have measured directly in the laboratory. Instead, it is a name for whatever drives the acceleration. Observations of distant Type Ia supernova, used as standard candles because of their consistent luminosity, showed that galaxies billions of light years away were dimmer than expected in a decelerating universe. They were not simply farther because of errors in distance measurement. Rather, space had expanded more than anticipated. The simplest explanation was that some form of energy permeating the vacuum exerted a negative pressure, counteracting gravity on large scales and pushing the universe apart faster. The concept of a repulsive pressure was not entirely new. Einstein himself had introduced the cosmological constant in 1917, seeking to hold the universe static against gravitational collapse. He abandoned it when expansion was discovered, later calling it his greatest blunder. Ironically, a constant energy of the vacuum turned out to be an almost perfect fit for the data 80 years later. If dark energy is nothing more than a cosmological constant, then it is a property of empty space, a fixed energy density that remains as space expands. This picture is mathematically simple and fits most observations with high precision, but it raises a deep theoretical puzzle. Quantum field theory tells us that the vacuum is not empty, but teeming with virtual fluctuations. When physicists attempt to calculate the energy of that vacuum, the result is enormous, many orders of magnitude larger than the observed value of dark energy. The discrepancy is so vast that it is often cited as the worst prediction in physics. How the energy of the vacuum is reduced to such a tiny but non-zero value remains unsolved. This mismatch between theoretical expectation and observation is the cosmological constant problem, and it highlights how poorly understood the nature of dark energy remains. Because of this difficulty, many researchers have explored alternatives in which dark energy is not a true constant but a dynamic component. One class of ideas involves scalar fields, similar in spirit to the Higgs field that gives particles mass. A scalar field rolling slowly down its potential could have an energy density that changes gradually with time, mimicking a cosmological constant today, but evolving in the far future. Such models are collectively called quintessence. In some versions, the energy density diminishes to zero, leading the universe back to matter domination. In others, it increases, leading to catastrophic scenarios such as the Big Rip. The challenge is that while these models are theoretically flexible, they lack independent evidence, and most fit current data no better than the simple constant model. Another possibility is that what we attribute to dark energy may instead be a sign that general relativity itself requires modification on cosmic scales. The equations of Einstein's theory have passed every local test, from the precession of Mercury's orbit to the detection of gravitational waves. But extrapolating them across billions of light years is a bold step. Alternative theories of gravity, such as FR gravity or brane-world scenarios, can produce acceleration without a cosmological constant. These approaches are attractive in that they might also connect to deeper frameworks like string theory, but they must be carefully tested against precision cosmological data. For now, none has achieved the simplicity and consistency of the cosmological constant. To characterize dark energy empirically, cosmologists use the equation of state parameter, symbolized as W, which relates its pressure to its energy density. A cosmological constant corresponds to W equal to -1. Deviations from this value would signal new physics. Surveys of supernova, the cosmic microwave background, and the distribution of galaxies all point to W being very close to -1, within a few percent. The data do not yet rule out mild evolution of W with time, but any change must be subtle. Planned observatories such as the Euclid mission, the Nancy Grace Roman Space Telescope, and the Vera C. Rubin Observatory will sharpen these constraints, mapping cosmic acceleration with unprecedented detail. Dark energy also leaves its mark on the growth of structure. While gravity pulls matter together to form galaxies and clusters, dark energy works in the opposite direction, stretching space and reducing the rate at which structures grow. By measuring weak gravitational lensing, tiny distortions in the shapes of distant galaxies caused by intervening matter, astronomers can trace how clustering evolves. Comparisons between the growth rate of structure and the expansion history serve as a critical test. If the two disagree, it may signal that dark energy is not a simple constant, but something more exotic, or that general relativity itself breaks down on large scales. One remarkable feature of dark energy is its timing. For most of cosmic history, radiation or matter dominated the energy density. Only in the last few billion years did dark energy become the leading component, driving acceleration. This coincidence, that humans live in an era when matter and dark energy are of the same order, has sparked debate. Is it a mere accident, or does it point to deeper physics? Some anthropic arguments suggest that only in such an era could observers exist, since galaxies must form before acceleration suppresses structure. Others propose mechanisms that adjust the dark energy density dynamically to values compatible with life. None of these ideas is universally accepted, but the question underscores how mysterious the emergence of dark energy dominance really is. Beyond its physical properties, dark energy shapes our ultimate cosmic destiny. If it is a true cosmological constant, the universe will expand forever, approaching a cold, dilute state in which all but the closest galaxies vanish from view. If it evolves differently, more dramatic futures are possible. A big rip in which every bound system is torn apart, or a slow fading if the energy density decays. The nature of dark energy thus decides whether time stretches on indefinitely or ends in violence. Dark energy also raises profound theoretical issues. In quantum mechanics, energy densities are linked to fields, symmetries, and vacuum states, explaining why the observed vacuum energy is so small yet non-zero may require new principles of physics. Some theorists invoke supersymmetry, which can cancel contributions to the vacuum energy, though no evidence of supersymmetric particles has yet been found. Others suggest that the vacuum energy is not a fixed constant, but an emergent property of spacetime, arising only in the context of gravity. These approaches remain speculative, but reflect the deep unease that physicists feel about leaving dark energy unexplained. The mystery also connects to the broader search for unification. String theory, which seeks to reconcile quantum mechanics and gravity, predicts a landscape of possible vacuum states, each with its own value of vacuum energy. In such a multiverse picture, different regions of space could have different values, and we happen to live in one where dark energy is small enough to allow galaxies and life. While controversial, this line of thought attempts to explain the smallness of dark energy through selection effects rather than precise dynamical mechanisms. Critics argue that it makes the theory difficult to test, but it illustrates the far-reaching implications of the problem. As observations accumulate, the evidence for cosmic acceleration grows stronger. Galaxy surveys now map millions of galaxies across billions of light years, tracing the imprint of baryon acoustic oscillations, sound waves in the early universe frozen into the large-scale structure. These measurements provide a standard ruler to track expansion. Combined with the microwave background and supernova data, they consistently point to a universe dominated by dark energy. While uncertainties remain, especially in the exact value of the Hubble constant, the overall picture of acceleration is robust. The practical impact of dark energy on our everyday lives is negligible. The repulsive effect is extraordinarily weak on small scales, far too small to overcome the binding forces of atoms, planets, or galaxies. Only across cosmic distances does it become apparent. Yet its discovery reshaped our view of the universe. Where once we thought matter was the primary constituent, we now know that most of the cosmos is in a form we barely understand. Dark energy, the agent of acceleration, accounts for about 70% of everything. This shift in perspective is as radical as the Copernican revolution that displaced Earth from the center of the universe. The accelerating universe has also influenced the philosophy of science. It illustrates how progress often comes not from confirming what we expect, but from data that resist explanation. The faint light of distant supernovae forced a revision of cosmology, and with it an expansion of imagination. Scientists now live with the recognition that the cosmos is stranger and more flexible than intuition suggests, that space itself can act like a medium with properties we barely grasp. On human timescales, the existence of dark energy changes nothing about our daily experience. Yet its implications for the future are staggering. If expansion continues to accelerate, then over tens of billions of years the sky will grow emptier until only the remnants of our local group remain. Civilizations in that far future will struggle to infer the true nature of the cosmos. Their telescopes will reveal a lonely island universe with no hint of the vast structures we see today. There is something quietly existential in this realization. The universe is not only expanding but accelerating, as if driven by a hidden hand. We do not yet know the identity of that hand, whether it is a simple constant or a sign of new physics. But we know that it shapes the ultimate trajectory of everything we see. To contemplate dark energy is to stand at the boundary of knowledge, aware that the greatest portion of reality remains veiled, yet still able to glimpse its influence in the faint light of distant galaxies. Chapter 4. The Big Freeze, a universe that fades away. Among the scenarios for the ultimate fate of the universe, the Big Freeze is both the most widely accepted and, in some ways, the most quietly unsettling. It does not involve a cataclysmic collapse or a sudden rupture of reality. Instead, it envisions a cosmos that simply grows colder, darker, and more dilute with time, until every source of usable energy has been exhausted, and all processes that sustain structure or life have ceased. This is the picture that emerges most naturally if dark energy is a cosmological constant, and if the laws of physics continue to operate as we know them today. The Big Freeze is rooted in thermodynamics. The second law states that entropy, the measure of disorder, or the number of microstates consistent with a given macrostate, tends to increase in an isolated system. The universe taken as a whole can be treated as such a system, and its evolution is a story of entropy relentlessly rising. In the early universe, conditions were hot and dense, but remarkably uniform, with small fluctuations. Over billions of years, gravity amplified those fluctuations, leading to the formation of stars, galaxies, and clusters. These structures represent local decreases in entropy, but only because elsewhere entropy increased even more. The net trend is always upward. The Big Freeze is the endpoint of this trend, a state of maximum entropy where no further gradients exist to drive change. To understand how the universe heads toward this fate, we must trace cosmic history forward. Stars are the engines that currently supply energy gradients. They shine by converting nuclear fuel into radiation, sustaining planets and life. Yet stars cannot burn forever. High-mass stars exhaust their fuel in only millions of years. Stars like the Sun endure for billions. The smallest red dwarfs, with masses only a fraction of the Sun's, sip their hydrogen so slowly that they can burn for trillions of years. These dwarfs will dominate the stellar population in the far future, but even they will eventually fade, becoming white dwarfs that cool over time into cold, inert black dwarfs. As galaxies age, their star formation rate declines. Already in our epoch, the cosmic star formation rate has dropped dramatically compared to its peak billions of years ago. Gas reservoirs are consumed by star formation or expelled by stellar winds and supernovae. In the accelerating universe, fresh inflows of intergalactic gas are cut off as expansion isolates galaxies and groups from one another. Over trillions of years, star formation dwindles to almost nothing. The night sky of the deep future will lack the brilliant, short-lived stars that now light up spiral arms. Only long-lived dwarfs will remain, glowing faintly in the dark. The Big Freeze is not only about the death of stars, but also about the fate of the structures they leave behind. White dwarfs will cool into black dwarfs, neutron stars will fade, and black holes will dominate the mass budget of galaxies. Gravitational interactions will slowly reshape stellar systems, ejecting stars into intergalactic space and driving others into the cores of galaxies. Black holes in those cores may merge, growing even larger. For epochs beyond human imagination, these remnants will define the cosmos. Black holes are especially important for the entropy of the universe. They hold immense entropy because their microscopic states, though hidden, are extraordinarily numerous. According to Stephen Hawking's calculations, black holes also radiate very slowly, a process now called Hawking radiation. For black holes of stellar mass or larger, this evaporation time is staggering. A black hole with the mass of the Sun requires about 10 to the power of 67 years to fully evaporate. Supermassive black holes at galactic centers, with millions or billions of solar masses, survive far longer, up to 10 to the power of 100 years or more. When the last of them finally vanishes, releasing a final burst of radiation, the universe will lose its most massive and longest-lived objects. What remains after this long process is a diffuse bath of low-energy photons, neutrinos, electrons, and perhaps stable dark matter particles. If protons are unstable, as some theories of particle physics suggest, they will have decayed long before, leaving only radiation and the lightest particles. If protons are stable, matter will persist in degenerate remnants and dark matter halos. In either case, the average temperature of the universe will asymptotically approach absolute zero. This does not mean it ever reaches zero, but rather that energy becomes so thinly spread that no organized structures or processes survive. The Big Freeze differs from other end-of-universe scenarios in its timescale. Unlike a Big Rip, which could in principle occur in tens of billions of years, or a Big Crunch, which requires a dense enough universe to reverse expansion, the freeze unfolds over intervals so long that human language struggles to capture them. The current age of the universe is about 13.8 billion years. The first stars will still shine for trillions of years to come, but that is only the opening act. The timescales of black hole evaporation extend to 10 to the power of 100 years or beyond. These numbers are so vast that they defy analogy. If the age of the universe so far were compressed into a single day, the Big Freeze would not arrive for a span longer than geological or even stellar timescales multiplied again and again. It is a future so remote that it becomes almost abstract. Yet according to our best theories, it is the most likely future. The thermodynamic perspective helps clarify why the Big Freeze is called the heat death. Heat death does not imply burning, but its opposite, the end of heat flow. In a maximum entropy state, temperature is uniform everywhere. No gradients exist, and therefore no work can be done. Stars shine because nuclear reactions maintain a difference between hot cores and cooler surroundings. Planets sustain climates because of the energy imbalance between starlight and space. Life depends on energy gradients to drive metabolism. In the heat death, all of these gradients vanish. The universe is not dead in the sense of being destroyed, but dead in the sense of being quiescent, inert, and unchanging. An important subtlety is that while entropy approaches a maximum, the number of accessible states is finite only within horizons. In a universe dominated by a cosmological constant, each observer is limited to a de Sitter horizon, a region beyond which signals cannot reach. That horizon has an associated entropy and temperature, extremely low but not zero. Within this horizon, the number of states is finite, and statistical mechanics implies that given enough time, rare fluctuations could occur. In principle, Particles could spontaneously assemble into complex configurations, even something as bizarre as self-aware observers, Boltzmann brains, arising briefly from the void. Such speculations are controversial, but they underscore how strange the late universe could be. The Big Freeze also intersects with the physics of particle decay. If protons decay, the matter content of the universe changes fundamentally. Grand unified theories predict proton lifetimes much longer than current experimental limits, but finite nonetheless. If decay occurs, atoms themselves will eventually disintegrate into radiation, accelerating the approach to heat death. If protons are stable, matter lingers in remnants for longer, but the overall trajectory remains the same. The universe grows colder and simpler until complexity fades away. It is worth emphasizing that the Big Freeze is not speculative in the same way as some alternatives. The Big Rip requires exotic dark energy with properties not yet observed. The Big Crunch requires a reversal of expansion inconsistent with current measurements. Vacuum decay requires physics beyond the standard model. The freeze, by contrast, follows naturally from the cosmological constant model that best fits existing data. While details about proton decay or black hole evaporation remain open, the broad picture is a straightforward extrapolation of known physics. For that reason, many cosmologists regard it as the default endgame of the cosmos. Still, there are puzzles within this picture. Why is dark energy so small yet non-zero? Why did it come to dominate only recently, allowing galaxies and life to form first? How does the entropy of de Sitter horizons relate to quantum gravity? These unresolved questions remind us that even the simplest seeming future rests on mysteries not yet solved. The Big Freeze is not only about astrophysics, but also about the deep interplay of thermodynamics, quantum mechanics, and relativity. On human timescales, of course, the Big Freeze is irrelevant. Stars like our sun will shine for billions of years, long after human civilization has changed beyond recognition or ceased altogether. Even the last red dwarfs will glow for trillions of years. The ultimate fate of black holes unfolds over timescales incomparably longer. Yet thinking about these futures alters our sense of the present. To realize that the cosmos tends towards stillness makes the dynamism we see today, the bright galaxies, the life-bearing planets, the brief flourishing of consciousness, feel all the more remarkable. There is a quiet existential weight to the Big Freeze. It suggests not an explosive finale, but a fading into silence. The universe will not end with a bang or a tear, but with the slow extinguishing of light, the dissipation of warmth, and the smoothing out of every structure into uniformity. For us, beings who live in a cosmos ablaze with stars, it is sobering to imagine a sky without them. Yet in contemplating that distant fate, we are reminded that transience is part of the story of existence, and that our brief moment takes place in one of the universe's rare epochs of brilliance. Chapter 5. The Big Rip, When Expansion Tears Reality Apart. Among the possibilities for how the universe might end, few are as dramatic as the scenario known as the Big Rip. Unlike the slow cooling of the Big Freeze or the speculative collapse of a Big Crunch, the Rip imagines a cosmos in which expansion accelerates without bound until it shreds every structure, from the largest clusters of galaxies down to atoms themselves. It is a vision of cosmic disassembly, a future in which not even the fundamental bonds of matter survive. The idea arises from the way cosmologists describe the mysterious force driving accelerated expansion, dark energy. In our best-fitting model today, dark energy behaves like a cosmological constant. It has a fixed density in space independent of time, and produces an equation of state parameter W equal to -1. This constant value fits current observations well. But if W is not exactly -1 and instead is less than -1, a very different fate awaits. Energy of this kind is often called phantom energy. Rather than diminishing as the universe expands, phantom energy grows denser with time, and its repulsive effect strengthens. When extrapolated into the future, phantom energy leads to extraordinary consequences. As its density rises, expansion accelerates ever more rapidly. The Hubble parameter, which measures the rate of expansion, does not decline toward a stable value, as in the cosmological constant case. Instead, it diverges in a finite time. In practice, this means the scale factor of the universe, the measure of cosmic distances, becomes infinite at a specific moment. That moment is the Big Rip. The progression toward this end would unfold in stages. Initially, galaxies beyond the local group would vanish over the horizon, just as they do in a cosmological constant universe. But in the Rip scenario, expansion does not stop there. Eventually, the gravitational binding of clusters is overcome. Galaxies within clusters drift apart. Later, the very galaxies themselves cannot resist the pull of expansion. Their stars are separated from one another as the structures holding them together are torn apart. Moving closer in time, planetary systems lose their cohesion as stars and planets are pulled from orbit. Approaching the final moments, stellar bodies themselves are ripped into individual atoms, and finally atoms are disassembled as expansion overwhelms even the strong nuclear force. The entire ladder of structure, painstakingly built over cosmic history, is undone in reverse. The timeline for such a disassembly depends on how far below -1 the value of W lies. If it is only slightly less, the Big Rip could be trillions of years away. If it is more extreme, the end could arrive much sooner, perhaps in tens of billions of years, not vastly longer than the current age of the universe. In either case, the Rip's defining feature is that the end comes in finite time, not as an asymptotic fading, but as a genuine deadline for existence. It is important to stress that the Big Rip is not inevitable according to present evidence. Measurements of distant supernova, the cosmic microwave background, and the distribution of galaxies all indicate that W is close to -1, within a few percent. While values slightly below -1 are consistent with the data, extreme deviations are not supported. The scenario remains speculative, but it is taken seriously because it arises naturally from a simple modification of the standard model. If dark energy is phantom-like, the Rip follows mathematically. The physics behind phantom energy is puzzling. In most field theories, energy densities decrease with expansion. A substance whose density rises instead creates instabilities and negative kinetic energies that are hard to reconcile with conventional quantum theory. Some models introduce exotic scalar fields or modifications of gravity to produce such behavior, but no consensus exists. For many theorists, the very strangeness of phantom energy is a reason to doubt it is real. Yet science is driven by evidence, and until data rule it out decisively, the possibility of a rip remains open. What makes the Big Rip compelling, beyond its exotic physics, is the imagery it offers of cosmic dissolution. In this scenario, the end is not silent or invisible but dynamic. Unlike the freeze, where galaxies and stars fade gradually into the dark, the rip would bring a sequence of violent unbindings. Structures that took billions of years to form would be destroyed in a fraction of that time. Galaxies that collided and merged over aeons would be sundered. Planetary systems that endured stellar evolution would be scattered. Even atoms, the building blocks of matter, would fail. It is as though the universe itself rebels against coherence, dismantling every level of order. The rip also highlights how sensitive the fate of the cosmos is to the properties of dark energy. A shift in W by only a small margin below -1 transforms eternity into a finite lifespan. This is an extraordinary illustration of how cosmic destiny hinges on numbers we are still struggling to measure with high precision. Efforts to pin down W more tightly through galaxy surveys, weak lensing, and improved supernova observations are, in part, attempts to learn whether the rip is even on the menu of possible futures. For now, the consensus is that dark energy behaves very much like a cosmological constant, and the big freeze is the more likely fate. But the rip serves as a reminder not to assume constancy in the face of incomplete knowledge. Just as the discovery of acceleration shocked cosmology in the 1990s, so too could future data reveal unexpected dynamics. The expansion of space is not something we can intuit. It must be measured, and its mysteries may yet deepen. The Big Rip also invites reflections about the nature of time and endings. It imagines a universe that ends not by fading into stillness, but by reaching a point beyond which there is nothing. In the mathematics of phantom energy, the scale factor diverges, the horizon shrinks to zero, and the universe ceases to exist in any meaningful sense. Unlike the heat death, where the arrow of time continues, but nothing interesting occurs, the rip halts time's story altogether. It represents a true finale rather than an endless coda. For living beings, of course, this is all unimaginably distant. Even if the rip were to occur in tens of billions of years, it is still far beyond the lifespan of stars like our sun or the timescale of human civilization. Yet contemplating it provides perspective. The very forces that now separate galaxies and sculpt the large-scale structure of the universe might one day erase all structure altogether. To live in a cosmos where such outcomes are possible is to realize how fragile order is, how contingent the universe's coherence may be. On balance, the Big Rip is a scenario that emphasizes both the power and the limits of science. It shows that by extrapolating from present data and theory, we can outline futures as astonishing as the tearing apart of atoms by cosmic expansion. But it also reveals how dependent those futures are on assumptions about physics we do not fully understand. Whether phantom energy is real or merely a mathematical curiosity, the fact that it can be considered at all is a testament to how far cosmology has come in a century. From Einstein's equations to the faint light of distant supernova, the path has led us to envision a universe that might not just end, but end abruptly, through the unrelenting acceleration of space itself. There is something existential in imagining such a finale. If the big freeze is a slow fading and the big crunch a collapse, the Big Rip is a rending, a refusal of permanence at every level. It is a universe in rebellion against its own structures, where nothing, not even the most fundamental bonds, is safe. To think about it is to confront impermanence in its most radical form, and perhaps to appreciate all the more the brief coherence of the present. Chapter 6. The Big Crunch, a Collapsing Universe. The vision of the universe collapsing into a final cataclysm has long fascinated both scientists and philosophers. Known as the Big Crunch, this scenario is the mirror image of the Big Bang. Instead of expansion continuing indefinitely, gravity eventually halts it, reverses it, and pulls all matter and energy back together. Space contracts, galaxies approach one another, and the cosmos ends in a state of enormous density and temperature. For a time in the 20th century, this possibility was considered a serious contender for the universe's fate. The foundations of the Big Crunch lie in the equations of general relativity. When Einstein's field equations are applied to a homogeneous and isotropic universe, the outcome depends on two critical factors: the geometry of space and the total energy density of the cosmos. If the density of matter and radiation exceeds a certain critical value, gravity overwhelms expansion and the universe recollapses. If the density is below this threshold, expansion continues forever. In a perfectly balanced case, expansion slows but never quite halts. In this framework, the destiny of the cosmos is intimately tied to how much matter and energy it contains. When Hubble's discovery of cosmic expansion became accepted in the 1920s, astronomers and theorists immediately wondered whether the expansion would go on forever or not. For much of the 20th century, estimates of the mass density of the universe were uncertain, leaving both eternal expansion and eventual collapse on the table. The Big Crunch seemed plausible because galaxies, clusters, and the large-scale structure of the universe all suggested substantial amounts of unseen matter. If enough mass existed, it might drag the cosmos back together in the distant future. The crunch gained further appeal because of symmetry. If the universe began in a hot, dense state, perhaps it was natural to think it might end in one as well. A collapsing universe could even lead to a cyclic model: expansion followed by contraction, followed again by a new Big Bang. Some cosmologists found elegance in such a repeating cosmos, with no true beginning or end, just an eternal cycle of death and rebirth. This concept resonates with ancient philosophies that imagined the universe as endlessly repeating itself in cycles of destruction and renewal. In the mid-20th century, measuring whether the universe was open or closed became a major goal of observational cosmology. Astronomers sought to weigh the universe by estimating the mass in galaxies and clusters. The more matter there was, the greater the chance of eventual collapse. Radio astronomy, galaxy surveys, and studies of galaxy motions were all pressed into service. For a time, the evidence seemed ambiguous. Some measurements hinted that the universe might be just shy of the critical density, leaving the door open for a crunch. Others suggested much less matter, pointing toward endless expansion. The debate sharpened interest in understanding the unseen mass later known as dark matter. Thermodynamics offers a compelling way to imagine a collapsing universe. As contraction proceeds, the cosmic background radiation, now cooled to a few degrees above absolute zero, would grow hotter again. Galaxies approaching one another would merge, and the collisions of stars and gas would release tremendous energy. In a contracting cosmos, the arrow of time still points forward, and entropy continues to rise. But instead of trending toward cold emptiness, entropy manifests as heat and radiation compressed into an ever smaller volume. Eventually, molecules are torn apart, atoms ionized, and even nuclei destroyed as densities soar. If contraction continues unhindered, conditions approach those of the early universe. Temperatures climb to billions of degrees. Densities reach levels where even the strong nuclear force can no longer maintain stable matter, and the universe returns to a plasma of fundamental particles. General relativity predicts that all of space could collapse into a singularity, a point of infinite density. Whether such a singularity can actually form depends on physics beyond our current reach. Quantum gravity may prevent infinities, introducing a new phase of matter or space-time itself. But from the perspective of relativity alone, the Big Crunch is the symmetric endpoint of cosmic evolution. The idea of a collapsing universe inspired speculation about rebirth. If singularities are not true endings but transitions, then the crunch might lead to a bounce, igniting a new expansion. In this picture, the Big Bang was not the ultimate beginning, but the aftermath of a previous collapse. Entire cosmologies have been built on this idea. Richard Tolman in the 1930s explored oscillating universes in which expansion and contraction alternate indefinitely. More recently, models from string theory and loop quantum gravity have revived versions of cyclic cosmology. In such views, the cosmos is eternal, not in stasis but in rhythm, passing endlessly through crunches and bangs. Entropy complicates this appealing vision. If entropy always increases, then each cycle would begin with more disorder than the last. Over infinite cycles, entropy would accumulate and the pattern would break down. Some modern cyclic models attempt to evade this by proposing mechanisms to dilute entropy between cycles or to reset conditions at a bounce. Whether such mechanisms are physically plausible remains uncertain. But the very attempt to reconcile thermodynamics with cosmic cycles illustrates how the crunch continues to spark deep theoretical debates. Particle physics plays a role in these discussions as well. If dark energy is not constant but dynamic, it could decay in the future, allowing gravity to reassert itself and drive collapse. Some fields invoked to explain inflation in the early universe might also govern the fate of expansion later. If such a field rolls down its potential energy curve and becomes negative, it would reverse the current acceleration and pull space back together. These are speculative ideas, but they highlight how intimately connected the fate of the universe is to the behavior of fundamental fields we do not yet fully understand. From the standpoint of observations today, the crunch looks unlikely. Measurements of the cosmic microwave background, baryon acoustic oscillations, and supernova distances all indicate that dark energy dominates and behaves much like a cosmological constant. That points to continued expansion rather than collapse. Yet these measurements only probe the recent past. The far future remains open, dependent on physics we cannot yet confirm. If dark energy is truly constant, the crunch is excluded. But if it evolves, especially in ways not yet detectable, the possibility remains. The imagined stages of a collapsing cosmos are dramatic to consider. As contraction begins, galaxies that once drifted apart would converge. The night sky would grow more crowded, filled with merging galaxies and brilliant starbursts. Over time, the background temperature would climb, bathing space in a glow increasingly hostile to life. Later, as contraction accelerates, the universe would become so hot and dense that stars and galaxies disintegrated, leaving only a seething plasma. In the final moments before the crunch, densities would exceed anything we can reproduce in laboratories, pushing physics into regimes beyond our current theories. From a human perspective, the crunch is both terrifying and strangely elegant. Terrifying because it envisions the destruction of all order in a violent collapse. Elegant because it restores symmetry between beginning and end. Where the big freeze stretches into eternity and the big rip disassembles structure, the crunch is a crescendo, a universe ending as it began in fire. Philosophically, it offers closure. The cosmos is not left to fade into silence, but concludes with a definitive finale. Even if it never happens, studying the crunch has been valuable. It motivated generations of cosmologists to measure the density of the universe, to search for dark matter, and to refine the theory of cosmic expansion. It encouraged models that linked the early and late universe, and it still inspires theories of cyclic cosmology. In this way, the crunch functions not just as a possible future, but as a driver of scientific progress. The true fate of the universe remains uncertain, and humility is appropriate. A century ago, no one predicted cosmic acceleration. Perhaps new physics will one day change the picture again, reviving the crunch or some variation of it. For now, the evidence points toward expansion without end. But the possibility of collapse remains a haunting alternative, a reminder that the cosmos is not obligated to match our expectations. And there is a final existential reflection. If everything we know is destined to fall back into a final moment of collapse, then all structures, from galaxies to thoughts, are temporary eddies in a sea that will one day surge back on itself. The Big Crunch offers a vision of impermanence at the grandest scale. To contemplate it is to feel the fleeting nature of even the universe itself, and to cherish the improbable span of time when stars shine and life is possible. Chapter 7. The Heat Death of Time, Entropy's Final Victory. The concept of heat death is one of the oldest and most enduring visions of cosmic destiny. It first emerged in the 19th century, decades before astronomers even knew the universe was expanding. At that time, scientists were grappling with the newly formulated laws of thermodynamics, which revealed that energy is conserved, that heat flows from hot to cold, and that entropy in an isolated system never decreases. Rudolf Clausius and William Thomson, later known as Lord Kelvin, realized that these principles applied not only to steam engines, but to the universe as a whole. If entropy always increases, then eventually all energy differences would disappear, leaving a cosmos without the ability to perform work. This prediction was dubbed the heat death of the universe. At the time, the idea was more philosophical than astrophysical. The scale of the universe was poorly understood, and stars were thought to be perhaps eternal. But the logic of entropy was difficult to escape. Even then, it suggested that the universe had a direction in time, a past of lower entropy and a future of higher entropy. This insight gave physics one of its deepest concepts, the arrow of time. Every irreversible process, from a cup of coffee cooling to the evolution of galaxies, is a manifestation of entropy's increase. Heat death is what happens when this arrow has nowhere left to go. Modern cosmology gives the idea new depth and specificity. The universe began in a remarkably low entropy state, despite being unimaginably hot and dense. This paradox arises because gravitational entropy behaves differently from ordinary thermal entropy. A uniform distribution of matter, though apparently simple, has lower entropy than a clumpy one, because gravity favors clumping into stars, galaxies, and black holes. Over cosmic history, the growth of structure has therefore been an expression of entropy increasing, not decreasing. The cosmic web of galaxies, the formation of stars, and even the emergence of life are all temporary episodes in the march toward higher entropy. Black holes play a central role in this story. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that black holes are thermodynamic objects with entropy proportional to the area of their event horizons. The entropy contained in a single supermassive black hole dwarfs that of all the stars and gas in its host galaxy. In fact, most of the entropy in the observable universe today resides not in the light and matter we see, but in the horizons of black holes. This makes them the dominant actors in the entropy balance sheet of the cosmos. Hawking also demonstrated that black holes are not truly black. Quantum effects at the event horizon cause them to emit radiation, a process now called Hawking radiation. For large black holes, the radiation is incredibly faint, and the timescale for evaporation is mind-boggling. A black hole of solar mass requires about 10 to the power of 67 years to evaporate fully. The most massive black holes, with billions of solar masses, take up to 10 to the power of 100 years. Yet however long it takes, evaporation is inevitable in standard physics. When it happens, the black hole releases its mass as radiation, further dispersing energy into the cosmos. In the heat-death picture, even these titans eventually fade into nothing more than low-energy photons and particles. Particle physics may accelerate the path to heat death. Some grand unified theories predict that protons, long thought stable, will eventually decay into lighter particles such as positrons and neutrinos. Experimental searches have so far found no evidence, but they place lower limits on the proton's lifetime, exceeding 10 to the power of 34 years. If protons do decay, then all ordinary matter will eventually disintegrate long before the last black hole evaporates. Galaxies, stars, and planets will dissolve into radiation and the lightest stable particles. Even if protons prove to be absolutely stable, however, the long-term trend remains. Matter becomes ever more diffuse, energy ever more evenly spread. In this final state, the universe approaches absolute zero temperature, but never reaches it exactly. Expansion continues to redshift radiation, stretching photons to longer and longer wavelengths. Neutrinos and electrons, if still around, drift apart into a sparse sea. The cosmos becomes a uniform bath of particles with virtually no structure. With no gradients left, no work can be done. In this sense, physics itself does not stop, but the variety of phenomena dwindles until nothing meaningful happens. An important subtlety is the role of horizons in an accelerating universe. If dark energy is truly a cosmological constant, the universe tends toward a de Sitter state, in which each observer is surrounded by a horizon beyond which events are forever inaccessible. This horizon has a temperature, though extremely low, and a finite entropy proportional to its surface area. That entropy places a limit on the number of independent states accessible within the horizon. Once the universe reaches this state, it can be described as thermally equilibrated within that finite set of possibilities. But statistical mechanics suggests that in such a state, extremely rare fluctuations are possible. Over unimaginable timescales, particles might briefly cluster into unlikely structures. One disturbing implication is the so-called Boltzmann brane paradox. In a heat-death universe, the most probable complex structures may not be galaxies or civilizations, but transient self-aware observers fluctuating into existence out of randomness, only to vanish again. While this scenario is deeply counterintuitive, it highlights the difficulty of reasoning about probability in an eternal, high-entropy cosmos. It also underscores that heat death is not only a physical idea, but a philosophical one, raising questions about meaning and existence in a universe stripped of regularity. Another speculative question concerns Poincare recurrences. In finite systems with bounded energy, states can recur after sufficiently long times. In a de Sitter universe with finite entropy, some argue that the cosmos must eventually recycle through previous configurations, effectively repeating histories. The recurrence timescales are so immense, numbers with more digits than particles in the universe, that they defy comprehension. Still, the possibility suggests that heat death may not be truly final, but part of a strange cycle of recurrence and fluctuation. Whether such recurrences are physically meaningful is debated, but they add nuance to the concept of entropy's final victory. From the human perspective, these scenarios are so remote that they seem almost abstract. The universe today is just under 14 billion years old. Heat death unfolds across timescales of trillions upon trillions of years, extending to powers of 10 that overwhelm imagination. By the time entropy dominates completely, stars will have faded, galaxies will have merged or dispersed, and black holes will have vanished. Compared with these scales, the entire history of life on Earth is a flicker. Yet contemplating heat death places our existence into a larger narrative, one in which order and structure are temporary, fleeting against the backdrop of thermodynamics. Unlike the violent finales of the Big Rip or Big Crunch, the heat death suggests no drama, only stillness. It is not an explosion or a collapse, but an erasure through dilution and equilibrium. The universe does not cease to exist, but ceases to change. For some, this makes it the bleakest of all scenarios. For others, it is strangely serene, a vision of the cosmos at peace after an incomprehensibly long journey. There are, however, profound scientific uncertainties. Dark energy may not remain constant. Quantum gravity, still incomplete, may alter the ultimate behavior of black holes or horizons. Particle physics may reveal that matter is unstable in ways we cannot yet measure. These unknowns mean that heat death, while the default extrapolation, is not guaranteed. Still, among the possible fates, it is the one most directly implied by what we currently observe. The existential implications of heat death are subtle but powerful. Time, as we experience it, is tied to entropy. In a universe where entropy has reached its maximum, the arrow of time disappears. Without change, the distinction between past and future loses meaning. To imagine heat death is to imagine the end, not only of structure, but of temporality itself. The universe would persist, but in a state where nothing happens and nothing could happen. And yet, in contemplating that quiet finale, we are reminded of the extraordinary moment in which we live. We exist during the rare luminous epoch, when stars shine, galaxies blaze, and complexity flourishes. This window of cosmic time is brief compared with what lies before and after. Heat death reminds us that we inhabit one of the few chapters in the universe's story when there is something to witness, something to think about, something to be. Chapter 8. Beyond Heat Death, Exotic Endgames. When physicists describe the far future of the universe, the heat death often appears as the most likely outcome. It follows naturally from the second law of thermodynamics, the steady cooling of stars, the eventual evaporation of black holes, and the accelerated expansion driven by dark energy. Yet physics, particularly when pushed to extremes, rarely permits only one story. The universe may hold surprises that take us beyond the quiet stillness of heat death, into more exotic and less intuitive endgames. These scenarios rely on speculative but serious ideas in cosmology and high-energy physics. They are not simply inventions of imagination, but logical possibilities drawn from theories that extend or modify what we know. One of the most striking alternatives is vacuum decay. Quantum field theory describes our universe as sitting in a particular vacuum state, defined by the configuration of fields that permeate space. But what if the vacuum we inhabit is not the true lowest energy state of those fields? In that case, it is a false vacuum, metastable rather than absolutely stable. Quantum mechanics allows metastable states to decay through tunneling. A small region of space could spontaneously transition to the true vacuum, forming a bubble that expands at nearly the speed of light. Inside the bubble, the laws of physics could be drastically different. Particle masses, charges, and forces might not resemble those we know. For any observer caught within its path, the arrival of the bubble would be instantaneous and final. There would be no warning and no possibility of survival. Calculations using the measured masses of the Higgs boson and the top quark suggest that our vacuum may indeed be only metastable, with an eventual decay possible. The lifetime, however, is thought to be vastly longer than the current age of the universe. Still, the possibility underscores how fragile our assumptions about permanence can be. Vacuum decay would make the heat death seem tame by comparison. Rather than a gradual fading, it is an abrupt rewriting of reality itself. Whether this will ever happen depends on physics we have yet to fully understand, particularly at energies far beyond those probed in particle accelerators. Another exotic scenario comes from cyclic cosmologies. In these models, the universe does not simply end with a crunch or a freeze, but transitions into a new beginning. The idea of an oscillating universe dates back nearly a century, when cosmologists realized that general relativity allows for expansion followed by contraction. In a cycle, the end of one phase triggers the birth of another. More modern incarnations involve ideas from string theory in which brains, extended objects in higher dimensional space, collide and separate, producing new cycles of expansion. Loop quantum cosmology also suggests that at extremely high densities, quantum effects may prevent singularities, causing a bounce instead of an absolute end. If such models are correct, the universe might not die once, but repeat endlessly, each phase with its own galaxies, stars, and perhaps forms of life. The challenge for cyclic models is entropy. If entropy always increases, each cycle should begin with more disorder than the last, preventing exact repetition. Some theories propose ways to reset entropy or dilute it across vast extra dimensions. Others argue that what we call entropy may behave differently under quantum gravity. Until these questions are resolved, cyclic universes remain speculative but tantalizing. They offer a vision in which endings are not truly final, but part of a grand cosmic rhythm. A different possibility emerges from the study of dark energy. If the energy that drives acceleration is not a constant but changes with time, the fate of the cosmos could deviate dramatically from the freeze or heat death. Phantom energy, where the equation of state parameter W is less than -1, leads to the Big Rip, tearing apart structures in finite time. But even less extreme evolutions could produce novel outcomes. If dark energy decays to zero, the universe might eventually resemble a cold, matter-dominated cosmos, rather than one dominated by horizons. If it turns negative, expansion could halt and reverse, leading to a crunch. More exotic behaviors, oscillations, sudden phase transitions, or interactions with other fields, remain possible in principle. Dark energy is so poorly understood that its role in shaping the ultimate destiny of the cosmos is still open to surprise. Another speculative endgame involves the breakdown of space-time itself. Some approaches to quantum gravity suggest that space-time may not be fundamental, but emergent, arising from more basic entities such as quantum entanglement or informational structures. If that is true, the far future might not be described in terms of expanding space and fading particles at all. Instead, the underlying substrate could undergo transitions we cannot yet imagine, dissolving space-time as we know it. This would represent not just the end of stars or galaxies, but the end of geometry itself, a finale where the very notion of location and time dissolves. The idea of Poincare recurrence offers yet another twist. In finite systems, statistical mechanics allows the possibility that after an unimaginably long interval, the system returns to a state arbitrarily close to its original one. If the universe is finite and its entropy bounded by the de Sitter horizon, then it could, in principle, recycle through its states, replaying histories. The recurrence times are fantastically long, so long that they dwarf even the timescales of black hole evaporation. But if they are real, the universe would not end at heat death. Instead, it would fluctuate endlessly, with patterns and structures reappearing by chance. One paradox of this idea is that the most common complex fluctuations may not be entire universes, but minimal conscious entities, so-called Boltzmann brains, that spontaneously arise, live briefly, and vanish. While unsettling, these possibilities highlight how poorly we understand probability in cosmology. Some theories propose that even before recurrence, fluctuations could produce temporary islands of order in a heat-dead sea. Tiny patches of low entropy might emerge randomly, giving rise to stars, galaxies, or even temporary observers. If so, our own universe could itself be the result of such a fluctuation. This idea is controversial as it raises questions about typicality and observation. Why do we see a vast, ordered cosmos rather than the minimal conditions needed for consciousness? The debate continues, but it underscores the philosophical depth of contemplating exotic endgames. There are also speculations that tie the end of the universe to the multiverse. If our cosmos is one bubble among many in an eternally inflating multiverse, then its end might simply be one event in a broader landscape. Vacuum decay could connect our region to another, or heat death might be irrelevant if inflation continues elsewhere, endlessly spawning new regions. In this picture, universes begin and end constantly, and our fate is local, not ultimate. The multiverse, if it exists, reframes endings as part of an infinite mosaic. From the standpoint of observation, none of these exotic scenarios can yet be confirmed. We cannot see beyond our horizon, nor can we probe energies high enough to test vacuum stability directly. Our best data fit the simplest model of dark energy, consistent with heat death. But science progresses by confronting the unknown, and history has shown that the universe often defies expectations. Just as cosmic acceleration was a shock in the late 20th century, so too might new physics one day reveal fates stranger than the calm silence of entropy's end. Exotic endgames also force us to reconsider what it means for the universe to end. Does a vacuum transition destroy reality, or does it create a new one with different laws? Does a cyclic universe truly repeat, or does entropy guarantee novelty each time? Do rare fluctuations mean that endings are never final, only phases in an eternal play of order and disorder? These questions blur the line between physics and philosophy. They show that the ultimate fate of the cosmos is not just a matter of equations, but of interpretation, of how we define existence and meaning in the context of infinity. From a human perspective, the possibility of exotic endgames is both unsettling and strangely liberating. They remind us that even the most established extrapolations, like heat death, are provisional, conditional on physics we do not yet fully understand. They reveal that reality may harbor surprises beyond our imagination, endings more abrupt, more cyclical, or more bizarre than our current models allow. And in that recognition lies a final reflection. We live in an era where the universe is intelligible, where its structure can be observed and described, yet where its destiny remains open. The exotic endgames remind us that uncertainty is not a flaw but a feature of science, a sign that we stand on the frontier of knowledge. To contemplate them is to accept that our universe may one day face outcomes beyond stillness, beyond time, beyond even space itself. And in that contemplation, we glimpse both the fragility of order and the boundless possibilities of a cosmos still mysterious at its core. Chapter 9. What observations can and cannot tell us. Every scenario for the end of the universe, whether the slow fading of a heat death, the violent collapse of a big crunch, or the abrupt rupture of vacuum decay, begins with the same raw material, astronomical observations. Cosmology is not spun from pure imagination. It is built upon light collected by telescopes, gravitational waves caught in detectors, and particles measured in observatories buried deep underground. Yet even with the vast reach of modern instruments, what we can know is limited. Our universe is finite in age, finite in the distance light can travel, and shaped by physics that may extend beyond our current theories. Chapter 9 is therefore about boundaries, what our observations can reveal with confidence and where they necessarily fall silent. The story begins with the expanding universe itself. The discovery that galaxies are receding from one another was observational, grounded in the redshifts measured by Edwin Hubble and Milton Humason in the 1920s. That expansion remains the foundation of all modern cosmology. Since then, astronomers have refined our measurements of the Hubble constant, the present-day rate of expansion, using multiple methods. Supernovae of type 1a act as standard candles, providing distance indicators across billions of light-years. The cosmic microwave background observed by satellites like COBE, DUMAP, and Planck encodes information about the early expansion and geometry of the cosmos. Baryon acoustic oscillations, sound waves imprinted in the distribution of galaxies, provide a standard ruler across space and time. Each method strengthens the conclusion: the universe expands. But even here, uncertainty remains. The so-called Hubble tension, a discrepancy between measurements of the Hubble constant from the early universe, microwave background, and from the late universe, supernovae and local distance ladders, illustrates the limits of our knowledge. The difference may be due to systematic errors in calibration, or it may hint at new physics, such as evolving dark energy or exotic neutrino properties. Observations tell us that the universe expands, but they leave open the fine details that may alter predictions for its ultimate fate. Dark energy is another example. The discovery of acceleration in the late 1990s came from careful observations of supernovae at great distances. Their unexpected faintness signaled that expansion had sped up. Subsequent evidence from galaxy surveys and the microwave background confirmed this acceleration. Yet despite 2 decades of increasingly precise measurements, we still cannot say whether dark energy is truly a cosmological constant or something more dynamic. All we can report with confidence is that the data are consistent with a constant, with deviations smaller than a few percent. The implication for the end of the universe is profound. A true constant implies heat death, while deviations open the door to other scenarios. Observations constrain the range of options, but they cannot yet close the case. Observations of structure formation provide another window into cosmic destiny. Galaxies form and cluster under the influence of dark matter and cosmic expansion. By mapping millions of galaxies, astronomers track how structure grows with time. Weak gravitational lensing, the subtle distortion of background galaxies by foreground mass, offers a complementary probe. Together, these methods test the balance between gravitational attraction and repulsive dark energy. So far, the data align with the standard cosmological model, but hints of slight discrepancies remain. Whether those discrepancies signal measurement difficulties or new physics is not yet clear. Again, we see both the power and the limits of observation. It can highlight tensions, but it cannot immediately resolve them. The cosmic microwave background remains one of our richest sources of information. The faint glow at a temperature of just under 3 degrees above absolute zero carries the imprint of the universe when it was only about 380,000 years old. Its pattern of hot and cold spots reveals the density of ordinary matter, the abundance of dark matter, the geometry of space, and the initial conditions that seeded galaxies. It also constrains the curvature of the universe to be very close to flat. That flatness, in turn, influences whether the universe could one day recollapse. Current observations show no evidence for strong curvature, making a big crunch less likely. But the microwave background cannot tell us how dark energy will behave in the far future. Observations of the past are not always predictors of what lies ahead. Another tool is the study of stellar evolution and nucleosynthesis. By observing stars at different stages of life, astronomers confirm that nuclear fuel is finite. Stars die, leaving remnants that cool or collapse. This knowledge underpins the Big Freeze and heat death scenarios. Observations of white dwarfs, neutron stars, and black holes all confirm that stellar processes cannot continue forever. Yet while observations confirm that stars fade, they cannot measure directly what happens on timescales trillions of years into the future. We infer that the cosmos will cool and darken, but inference is not the same as direct evidence. Black holes illustrate the limits of observation vividly. We can detect their presence through accretion disks, gravitational lensing, and now gravitational waves from mergers. We can even image their shadows, as the Event Horizon Telescope has shown. But Hawking radiation, the mechanism by which black holes slowly evaporate, is far too weak to observe directly. Our belief in it comes from theory, not measurement. If Hawking radiation is real, then black holes eventually disappear, leaving only radiation. If not, the late-time fate of the universe could be different. Observations today cannot settle the question. They show us black holes exist and interact, but not what becomes of them in 10 to the power of 100 years. Particle physics connects to cosmic fate in similar ways. Experiments in underground detectors search for proton decay predicted by some grand unified theories. None has been seen, and the lower bound on proton lifetime now exceeds 10 to the power of 34 years. That is reassuring for the stability of matter in the near term, but irrelevant for the universe's far future. If protons do eventually decay, heat death arrives more quickly. If not, it is delayed. Observations can push limits further, but they cannot watch a proton live for trillions of years. Here again, cosmic fate hinges on physics beyond observational reach. There's also the question of horizons. Observations tell us that the universe is about 14 billion years old, and that the observable universe is about 93 billion light-years across. But the observable is not the same as the whole. Beyond our horizon may lie regions we can never see, shaped by physics we can never measure. If inflation occurred in the early universe, then our observable patch is just one bubble in a far larger structure. Observations cannot probe beyond that bubble. We can infer, speculate, and model, but we cannot observe directly. The limits of observation set permanent boundaries on what we can know about cosmic destiny. Even gravitational waves, the newest messenger in cosmology, face limits. They carry information about black hole mergers, neutron star collisions, and perhaps the echoes of inflation itself. But detecting waves from the first instant of the universe or from the ultimate fate, trillions of years ahead, may always be beyond reach. Observations are powerful but bounded. They give us extraordinary confidence in the past 14 billion years, and modest confidence in the next several tens of billions, but fade into speculation beyond that. it is important to recognize the philosophical dimension here. Science is empirical. We build theories consistent with evidence and then extrapolate cautiously. Observations can tell us how the universe behaves within the range of our instruments, but the far future depends on extending those theories to regimes never tested. The Big Freeze, Big Rip, Big Crunch, and heat death are not observed outcomes, but logical continuations of models. Their credibility depends on how reliable those models are when stretched across timescales unimaginably longer than any direct experiment. Still, observations remain our anchor. They tell us that the universe expands, that it is filled with dark matter and dark energy, that its geometry is flat, that stars die, and that entropy increases. These facts constrain the space of possibilities. They make some fates, like a rapid recollapse, unlikely. They make others, like heat death, natural. They cannot tell us everything, but they prevent us from drifting entirely into speculation. The line between what we can measure and what we can only imagine is sharp, and respecting that line is what gives cosmology its scientific foundation. And there lies the existential reflection. Observations are finite, bounded by the light that reaches us and the sensitivity of our instruments. Beyond those bounds stretches the unknown. To live in this universe is to dwell between certainty and mystery, certain that entropy rises, that stars die, that expansion continues, but uncertain about the ultimate fate written in physics we cannot yet test. The telescopes give us clarity up to a point, and beyond that we step into the dark, carrying theories as lanterns. That mixture of knowledge and ignorance defines not just cosmology, but the human condition. Chapter 10. What the end of the universe means for us. The fate of the universe may seem far removed from human concerns. The timescales involved stretch beyond comprehension, from billions to trillions to powers of 10 so vast that even analogy fails. No civilization, however advanced, can reasonably expect to witness the evaporation of a supermassive black hole or the rise of entropy to its maximum. And yet, questions about the end of the cosmos matter. They matter because they reveal what physics can and cannot say, because they shape our understanding of time and existence, and because they place our fleeting human moment in the context of a grand, unfolding story. Science approaches the end of the universe with tools grounded in observation and theory. From telescopes, satellites, and detectors, we have evidence that the cosmos expands, that it is filled with dark matter, and that its acceleration is driven by something we call dark energy. From particle physics, we know that matter is not infinitely stable, that black holes are thermodynamic objects with entropy and temperature, and that quantum effects can transform even the vacuum itself. Extrapolated forward, these principles give us several candidate scenarios for cosmic fate: the Big Freeze, the Big Rip, the Big Crunch, and heat death, with more speculative possibilities such as vacuum decay or cyclic cosmologies. Each is a consistent extension of known physics, though none can yet be tested directly. What all these scenarios share is a reminder that the universe is not static or eternal in the form we know it. The stars will not shine forever, galaxies will not remain as they are, and even atoms may not be permanent. The apparent permanence of the night sky is an illusion of human timescales. On cosmic scales, the universe is dynamic, evolving, and transient. Our current epoch is not the baseline state of reality, but a brief phase. We live during a luminous interval when galaxies are active and stars still burn. In the fullness of time, this phase will end. Understanding this changes how we think about the present. When cosmologists describe the Big Freeze or heat death, They are not merely speculating about the far future. They are situating us within a trajectory, showing that our existence coincides with an unusual, richly structured period of cosmic history. For the first billions of years, the universe was too hot and chaotic for complexity. For the last trillions, it will be too cold and diffuse. We occupy a narrow window when energy gradients exist, when chemistry and biology are possible, when observers can emerge to ask questions. In this sense, the end of the universe matters because it frames the rarity of the now. The universe's future informs us that the conditions we take for granted, stars, planets, warmth, complexity, are temporary. They will not return once gone. This deepens the significance of our present moment. It makes life not an inevitable feature of the cosmos, but an extraordinary accident of timing, arising in the narrow corridor between fire and ice. The physics of cosmic fate also challenges us to think about time differently. Entropy provides the arrow of time, and heat death represents entropy's maximum. If the arrow of time depends on increasing entropy, what happens when entropy can increase no more? Some physicists argue that time itself becomes meaningless in such a state. Others suggest that time continues but without events to mark its passage. Either way, the end of the universe forces us to consider whether time is an objective flow or a measure of change. It highlights that our most basic intuitions about past, present, and future may be tied to the temporary imbalance of order in the cosmos. There are also implications for physics itself. Every scenario for the end of the universe tests the limits of our theories. Black hole evaporation probes quantum gravity, a framework not yet fully understood. Vacuum decay depends on the stability of the Higgs field, which links particle physics to cosmology. Dark energy, whether constant or evolving, remains the greatest mystery of modern physics. By contemplating the universe's end, we push against the edges of knowledge and confront the incompleteness of our models. The quest to understand cosmic fate is inseparable from the quest to unify the fundamental forces of nature. From a cultural perspective, cosmic endings have always shaped human imagination. Myths of destruction and renewal appear in civilizations across history. Floods that cleanse the world, fire that consumes it, cycles of birth and death. Modern cosmology transforms these myths into physics, but the emotional resonance remains. The Big Crunch echoes ancient visions of cosmic fire. The heat death resonates with images of fading and silence. The Big Rip with dismemberment and dissolution. Science does not erase these metaphors. It reframes them, grounding them in evidence while retaining their existential weight. For individuals, the thought of the universe ending may seem irrelevant, given that human lives last only decades and civilizations at best thousands of years. But the contemplation of ultimate fate offers perspective. It tells us that permanence is not the natural state of things. Change and impermanence are woven into the fabric of reality. The awareness of cosmic endings does not diminish our moment but enriches it, reminding us that life is precious precisely because it is temporary. It also raises profound philosophical questions. If the universe ends in silence, what is the meaning of its history? If time itself loses its arrow, what does it mean for us to live in time now? These questions do not have final scientific answers, but they show how cosmology and philosophy intertwine. The study of endings does not simply tell us about distant futures. It reshapes how we think about existence itself. The limits of observation ensure that we cannot know the future with certainty. Telescopes reveal the past light of galaxies, not the future trajectories of cosmic evolution. Experiments test particle interactions in laboratories, not over quadrillions of years. All our scenarios are extrapolations, conditional on theories that may one day be revised. Yet the very act of constructing them is meaningful. It shows that humans, on a small planet around an ordinary star, can grasp the outlines of the cosmos itself. We may not know which ending will come, but we know enough to imagine possibilities, and that capacity for imagination is itself extraordinary. There is also a practical dimension to these reflections. Our descendants, if they endure long enough, will face the consequences of cosmic change on shorter timescales. Stars age, galaxies merge, planetary systems evolve. While the ultimate end may lie trillions of years ahead, intermediate milestones, the death of the sun, the collision of the Milky Way with Andromeda, the fading of star formation, occur on scales not entirely beyond imagining. In this way, cosmic fate is not only a question of abstract physics, but also part of the long-term story of life in the universe. In the end, what the universe's fate means for us is less about prediction than perspective. It means recognizing that we live in a rare moment, in a universe that is temporary, evolving, and fragile. It means accepting that permanence is an illusion, and that meaning arises not from eternity, but from transience. Science provides the framework, but the human response is philosophical. To see beauty in impermanence, and to value the brief chapter in which we find ourselves. And so, the study of cosmic destiny becomes not just an exercise in physics, but a mirror for human existence. The end of the universe tells us that nothing lasts forever. Not stars, not galaxies, not even time itself. But it also tells us that within that impermanence, there is room for wonder, for discovery, and for meaning. We are part of a universe that writes its story in epochs and endings, and for a fleeting moment, we are here to read a few of its lines. If you're still awake, friend, thank you for traveling this far with me. The universe may be vast and mysterious, but right now you've made a tiny, warm place inside it to rest. If your mind wants one more gentle journey, there's another quiet video waiting for you on the channel. Press play and float along. If not, close your eyes and let the last starlight fade. Sleep well, and may your dreams wander among the stars.